Hello everyone, welcome to High Performance Computing Advanced Scientific Computing course. This is lecture 15, Outlook Quantum Computing in HPC. Since recently the quantum computing gets more focus and its application in this lecture, we will have talk in this regard. According to the outline, this is lecture 15 and it will be the last talk for me in this course. The next lecture 16, it will be epilogue, and Maurice will talk for that lecture. Let's carry on for lecture 15. Let's start with a review on lecture 14, solid object, finite element, and meshes. In the previous lecture, we had a brief discussion and talk about the detail of the finite element method, what technique available in the finite element method, and how the high performance computing working, and it's essential in these numerical method. We said in the finite element method, the domain of the problem, it's split to different size of the element and the approximate function used to find the governing equation. However, the method using is different. We talk about the variational method, about the residual method, and the different method to find the weighting function. Then we had talk about the element shape, how the element shape is important, and how we can select the suitable one. Then we went through the step we need to take in the finite element to solve a problem, how we should find the appropriate element, and then finding the function for the displacement and define the equations for the strain, stress, and then about the element matrix, and etc. Then we had example of comparison of the different method in the finite element. In the second part of the lecture, we had a few examples from the finite element method, especially for 3D, and how the computing is important in 3D for the finite element, which we have a large number of the equation with high iterative numbers to converge. So the parallel computing in the most cases is required. Also, we talked about application of the finite element, which is has a wide application in solid object and in fluid area. We said the finite element method, according to this application, it's the most powerful method among other numerical methods in solid object and finite element. However, it's more difficult and complicated to other method, and it has a more computation and mathematical work. We can say it's difficult method in comparison to the other methods. However, its power make it capable to solve more range of the problems, and so because we don't have analytical solution to for many problem, and because of the problem of the boundary condition, one of the most applicable method is the finite element method. However, for the complex geometry, large size of the problem, 3D, the parallel computing and HPC is required. This is the point we understood for the lecture with few examples. The outline of this lecture, it will be about the quantum idea, which is came from the quantum mechanics. We will have a look on the background in the physics in this area. Then we will talk about the quantum computing in the part 2. This lecture will have two parts, part 1 and part 2. Let's carry on in part 1 of this lecture. First part, we will talk mostly about the quantum mechanics and about the idea of the quantum and how it leads to quantum computing. Let's start about the background in the physics, how quantum mechanics started, and then in our time we have the quantum computing. Uh, we have basic concept and laws in physics as we know them from our education, the Newton laws, electromagnetism. Well, in the end of the 19th century, this is started. Usually, physics consists essentially of the classical mechanics, the theory of electromagnetism, and thermodynamics. Classical mechanics was used to predicting the dynamics of material bodies. Maxwell electromagnetism provided the proper framework to study radiation. Matter and radiation were described in terms of particles and waves, respectively. The interaction between matter and radiation were well explained by the Lorentz force or by thermodynamics. So all of these concepts made people believe that the ultimate description of nature had been achieved. So far, everything was fine, and it seems this belief or opinion regarding the physics was correct. But some challenges started and lead to some new experiment, new studying, and quantum mechanics. Let's start with the challenges in the physics and what challenges came and started. Relativistic domain. Einstein's 1905 theory of relativity showed that the validity of Newtonian mechanics ceases at very high speed, at speeds comparable to the light. So this was the first challenge, that we cannot use Newtonian mechanics laws for high speeds. Then microscopic domain. As soon as new experimental techniques were developed to the point of probing atomic and subatomic structures, it turned out that classical physics fails miserably in providing the proper explanation for several newly discovered phenomena. It thus became evident that the validity of classical physics ceases at the microscopic level and that new concepts had to be invoked to describe, for instance, the structure of atoms and molecules and how light interacts with them. So these are two most well-known challenges started in the physics, and you can see in this figure how we have these different classification based on the sizes: the classical mechanics, relativistic mechanics, quantum mechanics, and quantum field theory. This started from these challenges, and now what we have is this classification. Let's carry on about the quantum concept and quantum idea, how it started. The failure of the classical physics to explain several microscopic phenomena such as black body radiation, the photoelectric effect, atomic stability, and atomic spectroscopy had cleared the way for seeking new ideas outside its purview. The first real breakthrough came in 1900 when Max Planck introduced the concept of quantum of energy. Then in 1905, Einstein provided a powerful consolidation to Planck quantum concept. He figured out that Planck's idea of the quantization of the electromagnetic wave must be valid for light as well. Then, following Planck's approach, he determined that the light made of the discrete bits of energy called photons. Another seminal breakthrough was due to Niels Bohr right after Rutherford's experimental discovery of the atomic nucleus in 1911. Bohr introduced in 1913 his model of the hydrogen atoms. Then in 1923, Compton made an important discovery that gave the most conclusive confirmation for the corpuscular aspect of light by scattering X-rays with electrons. He confirmed that the X-ray photons behave like particles with momenta h nu over c, which nu is the frequency of the X-ray. So you can see here from 1900 and to 1923, for 23 years, there were new ideas came and concept in the quantum, which determine some phenomena that classical physics was not able to describe them. We can say these items presented in this slide, the most important concept which made this change in the classical of the physics and make the modern physics regarding the quantum and quantum mechanics. After these few challenges and the new determination of the some phenomena and the quantum concept, the quantum mechanics born. So there were two independent formulations of quantum mechanics. The first formulation, called matrix mechanics, was developed by Heisenberg, and the second formulation, called wave mechanics, was due to Schrödinger. From these formulation and the evidence from some experiment we mentioned in the previous slide, and the achievement and evidence, the only valid framework for describing the microphysical world is quantum mechanics. So far, we are talking now, so far we have only this framework to describing. And we have two equations for the quantum mechanics. These two different formulations, Schrödinger waves and Heisenberg matrix were shown to be equivalent. So this is the good news. And so they are equal. Combining a special relativity with quantum mechanics, Dirac derived in 1920 an equation which describes the motion of electrons. So you see everything is very quick from 1900 and now it's 1928. Many things change with the quantum mechanics concept. The Dirac equation to describing the motion of electrons, known as Dirac equation, predicted the existence of an antiparticle, the positron, which has similar properties but opposite charge with the electron. The positron was discovered in 1932. It's only 4 years after its prediction by quantum mechanics. In summary, quantum mechanics is a theory that describes the dynamics of matter at microscopic scale. In the lecture for the lattice Boltzmann, we had some detail and explanation about the microscopic, and mesoscopic scale, and we can see how the quantum mechanic is a framework to describing the microscopic scale. Quantum mechanics now is a course, is a field to studying, and it's wide area to studying the quantum mechanics in some program, master program in physics. They studying only field of the quantum mechanics. So by this it mean it's wide area and open area to studying. In this lecture, we only point to some very important challenges and how it lead to quantum mechanics. Now, after this concept from the quantum, let's look on the quantum computing, how the quantum mechanics and the quantum idea lead to quantum computing. It started from the qubit. A quantum bit is any bit made out of a quantum system, like an electron or photon. Just like classical bits, a quantum bit must have two distinct states, one representing 0 and one representing 1. There are many kinds of qubits, some occurring naturally and others that are engineered. Some of the most common types include spin, trapped atoms and ions, photons, superconducting circuits. So as you can see, we can have the qubits naturally, or also we can engineer it and build it. The quantum computing is a really open area. Many studying and research and going to developing this area, building the qubit. We have different category of the computing with the quantum computing. We will talk about it in the second part of this lecture. However, the qubit is the most important part in this computing and how it provides possibility to do the quantum computing. Here you can see in this figure how the location of the particle or the state could be different with 0 and 1, and with different phase we can have a different combination of the states for this, and we will talk about its application. So far we have the basic concept of the quantum mechanics, and now we can see what the probability of the state in the qubits. Let's look on two important concepts in the quantum mechanics and of course the quantum computing. Superposition, the first one, and the second one, entanglement. To understand this concept, let's look in the quantum description in the dictionary. When you Google it, you can see a discrete quantity of energy proportional in magnitude to the frequency of the radiation it represents. But we are not talking about the quantum. It's not like this description. There is no particle, there is no wave, and there is no cat. Here the cat is referred to Schrödinger cat, which has some different probability of a state. If you are interested, you can read about that. We have the wave function from the Schrödinger equation. This wave function calculating the probability of the measurement outcome. The Schrödinger equation solution to this equation is the possible things that system can do. But this equation, this solution has important properties. If we assume this function 1 and 2 are solution, we can have superposition of these two solutions with two arbitrary prefactors. This is the another solution. So it's important properties. That means if we have one or two solution or three, we can have superposition of them. This is the superposition. Superposition is not absolute term. That means if we look on the Schrödinger cat, we can say cat dead, alive, or superposition of the dead and alive. As we said about the wave function, if we have the wave function number 1 and 2, we can have superposition for wave function 3 and 4, and of course again we can have wave function 1 and 2 with superposition of wave function 3 and 4, as you can see here. So the superposition is important feature and make this possibility for a different state and different solution. After the superposition, let's look on the entanglement. Entanglement determines the correlation. That means from the superposition, from the different solution, we can have another solution, or we can have superposition of different solutions. But how many and which one is applicable? Let's look on the example of the particle. Assume we have a particle spinning. The spin in one direction positive, another direction is negative. So assume we have particle decays, and the one spin with positive direction, this is a negative, and the another possibility is this one. From the superposition, we know we can have this superposition of these particle decays for the spin. Entanglement is superposition, but superposition is not entanglement. If we measure a spin of one particle, we know a spin of another one because they are correlated. Entanglement does not depend on any selected to solve Schrödinger equation. So the entanglement, because it's providing this feature to have a correlation with different probability or different solution, it make it possible when you measure one state or one solution, you can have the answer for the another one because they are correlated. After this discussion about the superposition and entanglement, then let's look on the qubits, how they build. There are different type of the qubits. Here there are a few of them. The trapped atom and ions, it's working based off the energy level of the electrons. You can see the low energy could be zero state and the high energy could be the one state. The another one is a spin. The most quantum particle behave like little magnet, so this property is called a spin. The spin orientation always pointing either fully up or fully down, but never in between. So they're using this spin as a state 1 or 0. So this possibility from these features also possible to build the qubits. The another possibility for qubits is photons. The photon can be used as a qubit in several ways. With polarization qubit, each photon carries an electromagnetic field with a specific direction known as its polarization. Path qubit, the path a photon takes is another way to define a qubit. And time qubit, it's also possible to beat a photon qubit using its time of arrival. So this is a different description of the qubits that are engineered and could be used in the quantum computing. The another one of the qubits is superconducting circuits. When it's cooled to a low temperature, some material allow electrical current to flow with no resistance. So this feature also is applicable to use as a qubit. These four example of the qubits, you can read more detail about it and how they applied in the quantum computer when they're building these machines. So in the first part of the lecture regarding the quantum computing, we had some short history and background of the quantum mechanics and how it's lead to quantum computing idea. We talk about the qubits, and here there is a video talking about the qubit, what's a qubit, and I suggest you watch this video, and it has a good visualization of the qubits. So here we are finishing the first part of the lecture. Shortly after the break, we will back and carry on for the second part of this lecture.